All right, let's continue with this course, and we have finished already 2 classes, and we have covered most of the areas in magnetic field, which is the first chapter. We understand magnetic force between like current elements, definition of magnetic field, Biot-Savart law. We have also covered some of the simple applications, straight wire circular loops, and we have covered current loop as a magnetic dipole, dipole moments. Ampere's circuitry law, I'll still discuss a little on that so that we can get into the properties of magnetic field, the curl and divergence. We have discussed magnetic force on point charge current carrying wires already between current elements. Now, a lot of these parts are covered from Griffith, so you can go to the book and get a better feel of the matter. Now, this part I already covered, which is the, like, if we consider a magnetic field, the magnetic field for an infinite straight wire, like here in the figure, the current is coming out of the page in this one, which is this small dot. Now, what happens is, if you need to take integral of the B, so a line integration of a B across any of these circles, a line integration, then from Biot-Savart law, you get this one for B. This is the field at a distance S. And if we do a line integration of this one, this value is 2 pi s. So eventually you get this result. Now, this is also valid, mentioned in the last class also, even if you consider a cylindrical coordinate. So this equation is basically the Ampere's law. And a more generalized version of this one is something like this, where I is I enclosed. So that basically gives you, like, if we have a bundle of straight wires, each wire that passes through our loop contributes to mu 0 I, then those outside really don't contribute. So I enclosed stands for the total current enclosed by the integration path. If the flow of the charge is represented by a volume charge density, like current density J, then we can replace this one by this. So your right hand side, this one can be replaced by this one, whereas your left hand side, this one, can also be converted by Stokes' law to this one. And that gives us the curl of B, which is mu 0 J, and this one is your Ampere's law in a differential form. Further, we can, because we know from Biot-Savart law that B can be written in this manner. If we do a divergence of this one, then this factor can be split like this one on the vector analysis. And because this one becomes 0, because J doesn't depend on unprimed variations here. So your divergence of B becomes 0. This also has a implication that actually there is no magnetic monopoles. I'll get to that shortly. So if we compare between magnetostatic and electrostatic, what we have is Gauss's law and the curl of E is equal to 0. So this one we get from the electrostatic. So if you haven't studied electrostatic yet, it's a good time to go back and refresh it, read it. And these are also part of the Maxwell's equation. Further, from the magnetostatic, we just proved the divergence of B equals to 0 and curl of B equals to this thing, which is the Ampere's law. So these are basically important equations in terms of, like, these constitute the Maxwell's equations. And further, we also know that the force equation, which is also the Lorentz equation for in case you have electric field and a magnetic field both, so this case it's a particle is a charge which is actually moving at a pace v, velocity v. So it becomes like this. Now, for most of the cases, these problems are not that difficult, but some cases the geometry is too difficult to calculate the magnetic field. Then we can consider a concept like scalar potential, which we introduced during the electrostatics. So in electrostatic, like the field can be represented in terms of something like a minus a gradient of v. So the v is the scalar potential. Now it's definitely easier to handle a scalar because it doesn't have the problem of like various directions x, y, z, and dependence on the direction. Whereas a vector, like a field, has a direction, so that makes it more complicated for mathematics to deal with them. So we already know that for magnetic field, when we're getting into that thing, what we have is divergence of v equals to 0. Now it invites an introduction of a vector potential. So what we compared here is this one is like this one, whereas this one is equal to 0. So similarly here we use like because the curl of e equals to 0, so you can write it in this form. Similarly, because the divergence of b equals to 0, so you can pick up what we're doing here is we are picking up e equals to this one. So mathematically, if you put this one here, that becomes 0, so it's actually valid. Similarly, for divergence of b equals to 0, then we can pick up b equals to curl of a. So if you place this one here, that also becomes 0. So this one is valid. Now, this potential formulation automatically takes care of this one, as I mentioned, since the divergence of curl is always 0. So in Ampere's law, when we deal with Ampere's law, curl of B, then you're replacing B by this, then it becomes something like this one. Whereas the electric potential had a built-in ambiguity. You can add to V any function whose gradient is 0, which to say any constant without altering the physical quantity E. Likewise, you can add the magnetic potential any function whose curl vanishes. So similar to this one, you can actually add like B plus something you can add here, which is a scalar. Similarly here, so if you have this one, so curl of A equals to B, then we can for magnetic field also, we can like add. Likewise, you can add to the magnetic potential any function which curl vanishes. So here you can add something which curl will actually become 0. With no effect on the B. We can exploit this freedom to eliminate the divergence of A equals to 0. So this becomes equals to 0. Now, to prove this, we are considering that suppose our original potential A0 is not divergenceless. We add to it a gradient lambda, because as I mentioned, this curl needs to be 0. So this part's curl needs to be 0. Then the divergence of A becomes something like this. And it automatically becomes this part because we already know that this one is 0. Divergence of it. Now this is basically a Poisson's equation. So it comes down to this one and its solution are already known to us, which is this. Now divergence of A0 doesn't go to 0 in case to infinity. We will have to use other means to discover the appropriate lambda. So basically we can write by definition, B equals to this one, specifies the curl of A, but it does not say anything about the divergence. We are at the liberty to pick that as we see, like, so basically it's the same thing. So with this condition, like of A, new Ampere's law in terms of A, which is the vector potential, becomes something like this. And this is also a Poisson's equation. So what we're doing is we are converting the Ampere's law, which is in terms of B, the magnetic field, to the to A, which is the vector potential, and that is this equation. Now, if we solve this Poisson's equation, then what we have is something like this, which is in terms of J, which is the volume current density. You can write it in other terms also, surface or current directly. But it's clearly A is not as useful as V. Like, so the vector potential is not as useful or easy as the scalar potential. Realize that we're dealing with a vector potential here. So the potential is not a scalar. And naturally it's not easy. But it's still a vector, and although these are somewhat easier to work with. So other than Biot-Savart law, I think it's easier to calculate the B in this one. It'd be nicer if we can have a scalar potential, but that doesn't happen. Now, if we think about a problem like find the vector potential of an infinite solenoid with n turns per unit length, radius r, and current I, then this equation will come into handy. So we consider this factor and we convert this one by Stokes theorem to curl of A, and we know this one is already B, so it becomes B dot dA, which is basically the flux through the loop in question. Now here the Ampere's law we can write in this form, and we already know that B dot dl, this one, and now we consider this part here for this problem by this one, and we're using this function here. So basically what happens is we get the value of A from this one. So what we're doing is basically converting from this equation, we are using this one to calculate the value of the vector potential here for which is inside the radius of the solenoid, and this one which is outside the radius of the solenoid. Now in magnetostatic, because we just initiated this whole section of magnetostatics, what happens is like there are factors like J. The key factors are the volume current density, the magnetic field, and the vector potential. Now we already figured how to get one from the other. So in case of we start with a like J, then J can be converted to A, which is the vector potential with this equation. And also the relation between these two can be here, which is a sort of a Poisson's equation or a converted Ampere's law, this one. Similarly, the relationship between J with B is also directly, we can do it from Biot-Savart law, and it also gives, we can do it from the curl of B mu 0 I, which is the Ampere's law in differential form. We also figured out that divergence of B equals to 0. So we can figure this one out. So if you have J, you can actually figure out B and A. Now, if you have B, then you can also figure out A. And if you have A, then you can figure out B from this one, because B is curl of A as definition, and divergence of A equals to 0. Something to actually remember, refresh our memories as we go by. The boundary conditions of magnetostatics is also interesting, and some places in problems we may encounter them. So just like electric field suffers a discontinuity at the surface charge, the magnetic field is also discontinuous at a surface current. Only this time it is the tangential component that changes. So if we think about the integral form here for this problem, now for a wafer thin uh, pillbox straddling at the surface, what we get is this tangential below and above. This and this will be actually continuous. Similarly, if we think about a situation like this, and we use the Amperian law, Amperian loop here, then the component of B that is parallel to the surface but perpendicular to the current is discontinuous to the amount mu 0 K. So you have this amount coming in for this one. And in general, we can actually summarize these ones, which is the continuity of the magnetic field across this surface, can be expressed by this mu 0 K cross n. Now here n is basically an unit vector perpendicular to the surface, and it's pointing upwards. From this equation, so if we remember this equation and we know n and k, then we can actually get this equation, which is the parallel component and also the perpendicular component also. Now, the same is also true in case of, so in case of a vector potential, like in case of a scalar potential in electrostatic, the vector potential is also continuous across any boundary. So if we have this kind of a scenario, then we can also compare it for vector potential, and the vector potential is continuous across the surface. Because of the divergence of A, that this guarantees that the normal component is continuous, and curl of A equals to B in the form this one gives you this, which means the tangential component are also continuous. The flux through an Amperian loop of vanishing thickness is 0. So because we know already the behavior of B, then we can convert, or we can figure out the behavior of A across the surfaces. Whereas for the derivative of A inherits the discontinuity of B. So there is discontinuity of B, but A is continuous. Now only the derivative of A is actually discontinuous, like B from this one. So this is interesting, and some of the other things which is also interesting, I think this one more or less would gist up this chapter as we switch to the next one.